In this lesson, we will look at concentration and dilution. We have already investigated concentration in an indirect way, because when we look at concentration, what we're doing is showing exactly how much solute is dissolved in a given amount of solvent. Now, the majority of solutions are in the liquid state where water is the solvent. And so when we're in chemistry and we see the symbol AQ, which means aqueous, it means dissolved in water. So our solutions are mostly going to be water-based solutions. One thing to note is that solution chemistry is actually the most common way to work in the lab. So as you're going to see, we're going to be able to, once we know how to deal with concentration, we're going to be able to do so many more experiments, and you're going to see this unit many, many times from now until the end of your studies of chemistry. The concentration provides us with information about the relative quantities of solute to solvent, and it's always listed as the amount of solute per amount of solution. This is a general form of concentration, and there are many different units that we can use to express concentration. If you look around your medicine cabinet, you'll see some of these ways. So for example, on your toothpaste, you'll see a percent of mass by mass of fluoride in a sample of toothpaste. On a bottle of alcohol or on vinegar, you might see a mass per volume percentage. And when we were looking at solubility curves and we saw the mass of solute per 100 milliliters of water, that was also a form of concentration. Now, as chemists, we need to deal with the mole because how we relate substances to one another is with the unit of the mole. So we're going to use a special concentration called molarity. And the molarity, which is the chemist's concentration, is expressed in moles of solute per liter of solution. The general formula is C is equal to N over V. It's not uncommon to see the C here replaced with a capital M, so sometimes people refer to it as molarity, M equals N over V. We're going to use C. What's very important to note is that the volume when you're dealing with molarity is always going to be in liters. And this is really important to remember because a lot of the times when you're doing labs in chemistry, you're not going to be dealing with large quantities of solution like liters, you're going to be dealing with milliliters of solution. So it's going to be very routine for you to be converting from milliliters to liters, where you divide by 1,000. Now the units for molarity are varied. So the most basic form is to have the units being moles per liter, which is just using the moles on the numerator per liter in the denominator. Another unit that we can use for molarity is capital M. So you may have heard or seen in places and not really understood, it might say a 0.1 big M solution, or it might say a 0.10 molar solution. The capital M stands for molar. Now it's important for you to be able to switch between these two units and be very comfortable with them and recognize them as concentration units. Another form that you sometimes may see, and you will sometimes see it in textbooks especially because they're trying to save space, is you might see it reported as moles times liters to the -1. This is just moles per liter as a different format. As you know, when you have an exponent of -1, okay, that really is a variable that can be in the denominator. Let's try some practice problems involving our formula. In example 1, we have a solution that has 9 moles of sodium chloride dissolved in exactly 500 milliliters of solution. What is its concentration? So we've got C is equal to N over V. The moles that we have is 9. And our volume here is 0.5 liters. Now, as you're going to see when we start to prepare our own solutions, when you see a value like 500 milliliters of solution, this will be prepared in a special kind of flask. So you can take these as being exact values. In other words, you can take this as having 3 significant digits. So when we finalize our answer here and we find that it's 18, we can report it to 2 significant digits limited by the 9.0. So I can write 18 moles per liter, or I could write 18 molar, or 18 capital M. In example 2, the concentration of a hydrochloric acid solution is 6 molar. How many moles would exist in a 3 liters of the solution? So this simply requires us to rearrange the formula. We want to know the moles this time. So moles is equal to C times V. Our concentration is 6 and our volume is 3, already in liters, so we don't need to do a unit conversion in this case. And we find that we have 18 moles. And again, we've got 2 significant digits. In this next question, we're moving towards being able to prepare a solution of a given concentration. And this is something that I do on a very regular basis to prepare for experiments that students do. If I need a solution that is 3 mole per liter of potassium nitrate in order to do an experiment, and I've determined that based on all the numbers of students, I need 1,500 milliliters of solution, I need to figure out how many grams are required in order to make that solution. So this is going to require me to do 2 steps, and I'm going to use 2 very useful and common formulas. The first thing that I need to do is figure out how many moles are required in order to make this solution. So I want a 3 molar solution, and I need 1,500 milliliters, which is 1.5 liters. And so therefore I need 4.5 moles total. So I know how many moles are required to make the solution, but in order to actually prepare it in the lab, I've got to determine how many grams that is. So I need to use my second very important formula. Moles is equal to mass over molar mass. I rearrange it, so my mass is my moles, which are 4.5, times the molar mass of potassium nitrate, which is 101.11. And what I find is that I need 450 grams. Okay, so again, I would consider this to have 4 significant digits because I'm going to use a specialized flask to do that. So I'm limited to my 2 significant digits, which is why I rounded to 450 grams. In example 4, we've got a solution that's been prepared and we want to identify its concentration. So we've dissolved 0.35 grams and we've made a 65 milliliter solution. So again, this is 2 steps. I need to first figure out how many moles I'm dealing with by calculating using mass divided by molar mass. So I've got 0.35 divided by 169.88, which is the molar mass of the silver nitrate, and I find that I have 0.00206 moles of silver nitrate. And that is dissolved in 65 milliliters of solution. So that means that the moles divided by the volume, and my volume I need to put in liters, which is 0.065, and that gives me 0.032 molar silver nitrate.